Hi.
Hi, nice to meet you.
Yeah, nice to meet you too.
So this will be the Zoom for our session. So we'll have three talks. You're the first. And so welcome everyone to session 2 of our Sage Days. And it's my pleasure to introduce Stephen Diamond from the CVXPY team. He's currently with Gridmatic. Maybe you'll probably say a few words about what that is. Please take it away.
Thanks, Matthias. And thanks everyone for coming. So I'm going to be talking today about CVXPY, which is a package for convex optimization in Python, which I've been working on for many years. In terms of a bit of introduction, I did my PhD at Stanford in computer science, working on optimization and particularly software for optimization. Since then, I've moved on to Gridmatic, which is an energy startup where I use CVXPY every day. So that's great. Very optimization heavy technology stack. To start off, let me talk about what convex optimization is and lay out some definitions. When I say a convex optimization problem for our purposes, what I have in mind is the following. I'm minimizing some objective function f naught with variable x subject to inequality constraints fi of x less than or equal to 0, and then linear equality constraints. And these functions f naught and fi are convex. The formal definition is here, but generally you can think of this as bowl-shaped functions which have a single minima that's their global minima, just roughly speaking. So this is the particular standard form that we can have in mind for the moment. There are many variations of this. So instead of minimizing this, I could maximize a concave function, which is just the negative of a convex function. There are other kinds of constraints you can have, other kinds of nonlinear constraints. But in the end, it all can be converted back and forth. So why do we care about this class of problems? Because it is quite a restricted class, given the sort of things people are interested in these days. For example, deep learning is non-convex optimization. So why are we still interested in this smaller, more restricted class of optimization problems? There are a number of reasons. One is that the theory is very elegant and well developed. There's a lot we can say about these problems from many different perspectives. The duality theory in particular is super interesting. And in part as a consequence of that theory, there are algorithms that are really bulletproof, like really industrial level solvers that you can use to solve these problems reliably. So for example, in a control application, you might be solving a convex optimization problem every 30 times a second, right? And that needs to work every single time. And the technology has gotten to a point where that's possible. And most importantly, there's just a shockingly large number of applications for convex optimization, from more classical machine learning and statistics to control, as I mentioned, signal and image processing. This is something I worked on for a while. You might, for example, MRI image reconstruction, that can be posed as a convex optimization problem, all sorts of things. Energy systems, this is what I'm working on now. You might set up, basically, you could figure out how to do a minimum cost dispatch of all your different generators to all your different loads using convex optimization. Engineering design, there's some really interesting work using geometric programming, which is a subset of convex optimization for designing aircraft and all sorts of things. And then finance, this is actually the most common use case. So I would say that the greatest usage of our package is in the finance space. And it turns out that anytime a quant shop is actually trading, or it is actually forming a portfolio, they're solving some kind of convex optimization problem. And I'll show an example of that later. How do we solve these problems? There are a few different ways. One is to use one of the standard solvers, which are designed for some standard form, which could be, say, a linear program or an LP or a quadratic program, or other things like a second order cone program or semi-definite program. And the benefit here is that all the hard work has been done for you in terms of making the solver, but you still have to translate your problem into this format, which is not so difficult necessarily, but it can be error prone. And there are a lot of tricks that a novice wouldn't know. So I, as an expert, can pretty easily see how you get from a particular problem to a standard form. But someone who's just starting would really not know about this. Another option is to write your own custom solver. And in that case, you can take advantage of special structure. It can potentially be a lot faster in certain cases. It can be optimized for a particular computing environment. But this obviously is a huge amount of work and is going to require a lot of expertise. Now, the third option that I'll be focusing on today is using a convex modeling language. And the idea here is to have some user-friendly way of inputting the problem that is then compiled or translated automatically into the solver-friendly standard form. And I think of this as like, compiling into assembly from the human-friendly language into the machine-friendly language. There's a pretty long history of these convex modeling languages, going back to things like AMPL and GAMS. More recently, in particular with our group at Stanford, we've put out a number of modeling languages that are focused on convex optimization. The first one was CVX, which is in MATLAB. Miolane was not from our group; that was a different, but it's sort of also in MATLAB, somewhat different approach. CVXPY in Python, and there's also convex.jl in Julia, and CVXR in R. And these are all sort of based on the CVX design. The role of these modeling languages is twofold. One is to check and verify problem convexity, and the other is to convert into the standard form, as I mentioned before. And these two functions are actually coupled in a very interesting and clever way in the design of these systems. I'm not going to talk about it in any detail, but I'm happy to take questions. The way we verify convexity is using something called discipline convex programming, or DCP. This is a system for constructing expressions with known curvature, essentially. So all your expressions are going to be either constant, affine, convex, concave, or unknown curvature. So it's a sufficient condition for convexity, but not a necessary condition. And we've extended this with different work. So with other types of things. So for example, log convex, which is for geometric programming, and also quasi-convex, various things, but this is the general idea. Expressions we view them as expression trees, and at their leaves, they have variables, constants, and parameters. And then all these leaves are combined through a fixed library of functions with known properties. So known curvature, known monotonicity, known sign. And this is an important part of the design of the system, that you can't provide user-defined functions. You have to use a function library. And it was a little bit interesting, with CVX was built, it was assumed that everyone would be interested in contributing new functions, and it was designed to make that very easy. In the end, essentially no one did. So when I did CVXPY, it's actually not that easy to add a function, but actually now we've had many people contribute them. And I think this is really just a function of the different ecosystems for open source. So being on GitHub. So we have had quite a lot of contributions over the years. But in the end, it isn't too many functions, like maybe 100. And there's a website I made many years ago where you can look at this called dcp.stanford.edu, and it has different things like a quiz and an analyzer. I made it for the convex optimization class, but something you can look at if you're curious about this system. So CVXPY, I've been working on that for about 8 years, and we've had many, many contributors since then, some of whom are here. It uses a particular version of DCP. It's open source, it's Apache v2, and it is a variety of open source solvers that it comes with. One difference from CVX was support for parameters, which is sort of a small thing, but it had a lot of interesting consequences that I'll get to later. And we've been really gratified to see the uptake for this project. I mean, it's just really nice to see so many people using it in so many different situations. The main solvers that come with CVXPY are ECOS, which is a cone solver and interior point solver for second order cone programs. SCS is also a cone solver, but it's more of a first order method. It's ADMM, and that handles also SDPs. And then OSQP, which is a first order QP solver. And those are the three that come with CVXPY, all open source, but we have interfaces to just many, many, many others, more than these, like 10 or 15. And a lot of those have been contributed by the community, which is great. Here's what CVXPY actually looks like. Here's our optimization problem. So we have a least squares term here, right? Least squares, sum of the squares of ax minus b. And then we have an L1 regularization, so the sum of the absolute values of x with some parameter gamma in front. And then we just have some other stuff. So this entries of x have to sum to 0. And then the L infinity norm of x is constrained as well. So this might be some kind of constrained lasso problem. And we designed CVXPY to make the translation from math into code as clean as we were able to within the constraints of it being in Python. Here you get started by defining a variable, right, which is assigned to x. And n here is some dimension defined outside. Then we start building up the cost function, or the objective. This is, of course, matrix multiplication in Python, and A would be something like a NumPy array, and we've overloaded all these arithmetic operators so that they become CVXPY expressions. And then sum squares is one of those library functions that I mentioned that are built into CVXPY. So norm is another one, L1 norm. And then this is our cost function, and then you can minimize or you can maximize. Those are the two options. So here we're minimizing, that gives us our objective. And the constraints are similarly defined using operator overloading. So here we have the CVXPY sum function applied to x, and then equals is overloaded, and less than equals is overloaded over here. So we get a list of constraints. We get our problem. You call solve. And notice here, there are no arguments to solve. And that's something that comes out of this focus on convex optimization, because at least in theory, with a convex problem, it doesn't really matter what solver you use. If there's a unique solution, then you should be able to obtain it through any means with very high reliability. Versus for non-convex problems, it would depend, your outcome would depend on what solver you use, most likely. As a side effect of calling the solve method, it populates the value field of all the variables and also the dual value field for all the constraints. And that's how you can get the solution. So that's the basic idea with CVXPY. I'm actually going to skip this one. Here's an example of portfolio optimization, which I mentioned before. This is probably the most common use case of convex optimization these days. In portfolio optimization, we have a portfolio allocation vector, W, which is telling you the fraction of your total portfolio that is in each asset, each of the n assets. Use some set of allowed portfolios, which is a convex set. For example, it might be that you can only have non-negative holdings of an asset, which is called a long-only portfolio. Another one that is pretty common is that you have a constraint on the L1 norm of the portfolio, and that's called a leverage constraint. And different funds, for example, will have very specific numbers, like that has to be 3 halves or like something like that. That's another very common way to run a fund. We have a risk aversion parameter, which is giving us our risk-adjusted return. So the general idea here, roughly, is that mu is the expected return of all the different assets. And so this is the expected return of our portfolio. And then sigma is the covariance, roughly again, the covariance of the assets. And so, you know, we're adjusting, this is, yeah, a sort of risk-adjusted return. And we want to vary gamma to get a trade-off between risk and return. Here you can see that trade-off curve for a portfolio with 10 assets. Each of these assets is plotted here. So each red dot is one asset with a particular expected return and a particular standard deviation of return. Right? And the magic of portfolio optimization is that you can, for a particular risk budget, by combining all these assets and exploiting their correlations, you can do better than any individual asset, right? So this green line is what I get for different values of gamma, the different portfolios that I construct in this way. And this is the riskiest asset. So this is the one case where the asset corresponds with that trade-off curve, because you can't get riskier than being all in on the riskiest asset. But otherwise, it's a Pareto improvement. And here I've highlighted two particular points on the curve, which you can see here. So gamma equals 1.05. This is higher risk aversion. So the mean of your expected return for your portfolio is lower than for this riskier case with gamma equals 0.29. But the returns are more concentrated. So the standard deviation is lower. And at the other end, you could have a higher expected return, but you're going to have more risk, right? Fatter tails, etc. So that's the basic idea of portfolio optimization. This is called, this is essentially Markowitz, if you've ever heard of that. Dynamic energy management. This is an interesting area that I've been learning a lot about at my new job at Gridmatic. And the idea in this example is to show an object-oriented design, an object-oriented way of using CVXPY. This is something I think is very cool. It's basically putting different pieces of the optimization problem in these different objects that all get assembled, you know, to form this bigger problem. It's, I think, a nice way of handling complexity that's sort of taking advantage of the features of Python. In this case, we have different kinds of devices that are exchanging power over certain interfaces and planning out over multiple periods. So let's say every hour of a day. We have generators which produce, you know, some power within some range at a certain cost. We have loads, which usually loads are fixed, but there are other kinds of loads which can adjust based on the economics of the situation. We have storage systems, right, which can either be producing and putting out power or taking it in. And then other things that we could model if we wanted, like the losses on a transmission line. And the concept in this example is that each device has an objective function and constraints. And then we just have a certain way of ensuring power balance. This is not important. The power balance constraints. This is a quite simple model of energy, more simple than people would use in most cases, but it's one that's easy to talk about. And the goal is to minimize the total system cost to produce the power schedule. And here, there's a very cool rule for the dual variables, which is these provide what are called locational marginal prices. And you can actually look these up. So this is sort of how the power system works. It's a little more complicated than this. This is the general idea. And if you look up CAISO or ERCOT, you can go to their website and you can actually see these locational marginal prices, which generally are published every 15 minutes. And it is in fact solving usually a linear program or something like that to get these. So the cost of energy for a particular device or particular location. Here's a little baby example. We have a generator, a battery, and a load. The load is fixed but evolving over time. So you can see here what the load is demanding. The generator can produce power within a certain range, but the more power, the more expensive it is. And then the battery can do what it wants. There's no cost to it, but there's a certain constraints on how much it can discharge, and how much it can hold. So you can see here sort of interesting interactions between all these things. The battery charges up when the load is lower, right? So when there's this dip here and there's this dip here, the battery is charging, and then it waits for a while, and then it discharges at this peak. And the generator is providing a lot of power for a while, and then providing even more power at this peak. And then you can see the locational marginal price, which is incentivizing all this behavior. It's lower when the demand is lower, and then it starts going up as the demand increases. And it's interesting here, you can see how the battery is smoothing out the prices because the load isn't fixed. Well, actually, yeah, the load is not fixed, but using the battery, it's able to keep the generator at a fixed level. And so the total cost for this period is fixed. Then eventually it's too much load and price starts to go up. Here's what this looks like in code. We define all these different objects. So for example, a fixed load with a power schedule, like I showed you. The generator has some maximum amount it can produce, and then usually it's a quadratic representation of the cost function. So the two terms of the quadratic. And then storage has different parameters, a total amount it can store. And then this just we're saying there has to be power balance between these three, so no power is created or destroyed other than through the system, these different devices. And then we optimize it, and at the end we get the different schedules and the price. So this is a fun package called CVXPY. Again, it's a little bit of a simple model. There are more sophisticated models that you would use for in the real business, but it shows what you can do with this sort of object-oriented approach. Now I'm going to talk about two more recent works that have built on CVXPY in different directions. One is differentiable on the topic of differentiable programming. So differentiable programming is essentially a perspective on neural networks. So the idea here is that we view neural networks as essentially the idea is you're using taking gradients, doing back propagation to train these neural networks. And more broadly, there's this idea of differentiable programs where we have these different components that are all differentiable that we combine together. And so the idea is that your whole program, whatever it is going to be differentiable. And this allows us to be more creative about the kinds of things that are present in our program, the kinds of atoms that we have. And in particular, one kind of atom we can have in this is a convex optimization problem. And I'm going to explain how that works. And people call this sometimes implicit layers. There's another kind that's pretty popular actually, which solves differential equations. That's actually quite popular now. But this is for convex optimization problems. So the idea here is we have a convex optimization problem that's parameterized by something, some theta. And right, so you can see it's just the same standard form as before, but we also have this parameter that's defining these different functions, and then also can be defining the linear equalities. Here's a baby example just to illustrate the point. We're minimizing x minus 2 theta squared, right? I mean, of course, we know what the answer to that is, but this is an example of a parameterized convex optimization problem where theta is our parameter. And so each choice of theta induces a new optimization problem. And the idea is that we're going to interpret the optimization problem overall as a mapping from theta to a solution x star. And in our example, the mapping is theta to 2 theta, right? X star is 2 theta. But generally, you're going to have problems where you can't write the solution down analytically. Now, from a more mathematical perspective, there are like a lot of subtleties here. You know, for example, convex optimization problems don't have unique solutions necessarily. So you could think of this more as like a set valued thing if you wanted. And even if when it is a unique solution, it's by no means, you know, not guaranteed to be differentiable except under certain additional assumptions. But we were kind of inspired by the spirit of deep learning, which is to just try and use the chain rule and just see what happens. So there was a paper that about sort of more of the details and how this all works by a number of people. The basic idea is that you're implicitly differentiating the KKT conditions. That's generally the approach we take. Yeah, so there's different ways to do this more efficiently and less efficiently. And as I said, different subtleties about cases when it's not actually differentiable. But in the end, we just use the same procedure in every case and see what happens. Right, so of course, for our toy example, we know that if it's 2 theta is x star, then that's very easy to take the derivative with respect to theta. But again, when you have something like a quadratic program or something like that, where it's not analytical, this is actually, I think, a pretty powerful framework. And it's been very interesting for research. We looked at different applications, particular for learning control policies that are pretty interesting, like approximate dynamic programming applications. Yeah, so there's different papers on that if you go to Stephen Boyd's website, if you're curious. Here's what it looks like in code. We define a parameter theta, which is just another CVXPY object. We define the objective and the problem as before. Before we solve it, we have to set the value of theta to define the problem. And then we solve with this requires grad equals true. This is just a PyTorch thing. It's a PyTorch syntax. It tells CVXPY that you care about taking the gradient later on, so it's going to store more things than it would normally do so that it's able to take the derivative later. Then you do problem dot backward, which is going to compute that gradient with respect to theta. And that's pretty much it. There's a lot of, I think, cool stuff under the hood. We set this up in a way where essentially it generates down, basically the problem is compiled into this very efficient form, which is just a linear function, then solving a standard form cone program, then another linear function. And so the modeling language CVXPY is totally removed itself from the picture once it's compiled. And this had a number of advantages. It made things much more efficient to compute. And I'll show you later another interesting thing came out of this, which is a very nice approach to code generation. This is all implemented in CVXPY layers, which is also open source, and it interfaces to both PyTorch and TensorFlow, and there's some preliminary work with JAX. And it's all very straightforward. You just plug your problem into this CVXPY layer object and define the parameter inputs and the variable outputs, and then you can put this in your neural network, your differentiable program. CVXPY Gen, this is something that I'm very excited about. And in very recent work by Max Schaller. And the motivation here is that for different embedded applications, it's desirable to have a low level or C implementation. You don't want to have a Python interpreter running on your drone. You just want a simple C program. And okay, so then the question is, how can we get some of the benefits of these convex modeling languages given this restriction? And one approach is to define the problem in a high-level language and then generate the low-level code from that problem description. And this is an approach taken in a variety of places long before what we did. For example, in Casati, and then CVXGen. And it's actually been used like quite widely. And these are just examples that I know of. There are many others, but CVXGen was used by SpaceX, and then also on one of the Mars rovers. I'm not sure which one. So it's a very useful approach. CVXPyGen is again, very recent work. It builds on CVXPy. It generates flat C. So far, it has 3 different interfaces to solver interfaces. So OSQP, SCS, and ECOS. And it's the first generic code gender that we're aware of that supports second-order cone programs. CVXGen was for quadratic programs. And it supports a lot of different features from C that can be quite useful in these embedded applications. For example, warm starting, where you input the solution to a previous problem into your current problem. That can speed up a lot of these algorithms quite substantially. And it's also a way of making a custom solver that can be called by CVXPy. That's another perspective on it. It's like a JIT compiled solver. Here's what it all looks like. You import CVXPy and CVXPyGen as a separate package. You define your variables and parameters, and you have to give them names because that's how they're interfaced with through the generated code. And then you define your problem as usual, and you just call a generate code function, provide the destination, and it'll just generate, and then I guess the solver as well. And it'll, if you want it, and it'll just generate a nice folder of C code and a make file, all these things. It's really encourage you to check it out. Yeah, and this was actually, there was a nice connection between CVXPy layers and CVXPyGen, which was through this, like this way we compile the standard form where the modeling language is totally out of the picture. And it's just, everything is just basically the mapping from parameters to the standard form problem is a linear mapping. And we do that by imposing certain restrictions on how you can use the parameters, similar to the DCP rules that I described, which are for the variables. And this was all put to the test on a drone, on a quadcopter, which you can see here. And it was compiled, the code was generated, then compiled on a ROS node, and it ran at 30 Hertz. And it works. So we're very excited to see what people do with this. I think there will be a lot of cool applications. In summary, the main things I hope you take away is that Python or convex optimization is very easy in Python with CVXPy. It's very easy to specify these problems and verify convexity. I showed you how object-oriented design can be mixed in with the CVXPy problem construction. And 2 applications more on the research side, for one for differential programming, the other for code generation. I encourage you to take a look at cvxpy.org, or this is a CVX group that has CVXPy layers and CVXPy gen. And that's all.
Thanks very much. And we have time for questions. Yeah, I have a few comments at least. What I've found particularly interesting about CVXPY as a, wait, you say CVXPy? Yeah.
Yeah, CVXPy.
Okay, CVX. I'll learn that. CVXPy. As a rewiring step now. So I was particularly interested because of the problem transformations aspect that you have. Yeah, so you have like as objects, you have problem transformations, so kind of like maps that go into both directions. Yeah, and so that's something that I believe is missing in many modeling systems that are out there for optimization, where all of that, let's say, transformation knowledge is kind of hidden in implementation details and is not exposed, at the right mathematical level. And so that's, I think, what makes CVXPY a particularly good fit for Sage, because it's Sage is, structured maps all the way, right? So that would be a very interesting way to have a rich an expressive way of writing down, let's say, maps from real spaces to real spaces, and then to have automated reasoning about convexity and stuff like this. And so this way, of course, as you know, one can model convex sets via sublevel sets and so on. And so I think that's a very powerful tool, and so I'm looking forward to integrating CVXPY, CVXPy into Sage. So there's some preliminary work already. And I'll build slowly the connection to the next speaker. So I've seen that CVXPy also has initial support for integer optimization via some solvers, right? And so in particular, recent development in SciPy is that they now have real optimization solvers, HiGHS, made by Julian and his group, and so that's already available also as a solid backend in the CVXPy, and so that's the first and quickest integration route for us to give high performance LP and MIP solver to Sage, basically replacing our current default that is just GLPK. So Julian, a question, a comment?
Yeah, I've just got a couple of comments, but the questions for Stephen. First of all, we skip over the fact that when you've got integer variables, of course, you're no longer convex.
Yeah.
But I kind of know what you mean. Your energy example, again, what happens when you get to unit commitment? You just had one generator. Unit commitment means integers, doesn't it? Are you going to handle that?
Yeah, I mean, CVXPy handle, you can plug in integer variables, Boolean variables, and that just gets passed along to the solver. I mean, it's not as nice a story, but I think it's still useful to have all the modeling structure there.
Okay.
That's something that we're trying to build out more of, is different, more interesting sets or non-convex sets, and then also there's different things that the MILP solvers, for example, those interfaces need that the convex solvers don't. So I do think there still is value in the DCP approach. We call it like mixed integer DCP. I think it's still a nice way of defining your optimization problems, but you're certainly right that there are many situations where integer programs arise. But even for the energy example, it depends. Like the way I've actually learned now how they do it in reality, and they tend to break it up a bit. It seems like they will have a unit commitment stage, and then they'll have, but anyway, it's complicated. But yeah, certainly it's true. In most cases, you would have used the integer variables as well. Yeah.
And my other comment is when you're doing your differentiations through CVXPY, you illustrated it with an inequality problem. What happens with inequality problems where you get to breakpoints?
Yeah, so this is an example where there's issues with the definition of the derivative, and this, yeah. So we really went with sort of the general spirit of the neural networks, which is just to not worry and just see what happens. So this was really motivated by this trend of research in implicit, they call it implicit layers or various things like that. So this was our contribution to that topic. And yeah, there are many cases where mathematically it's not really clear what exactly is happening. But I guess the best we could do is when the derivative is defined, that is what we're computing. And in other situations, it's doing something hopefully reasonable. Yeah. But people really like to just try it. People really like to just see what happens with these layers.
Thanks.
Yeah, reacting to that, it's probably not too hard to regularize the problems so that they do get additional smoothness. And I suppose, but perhaps in the long run there needs to be a connection to kind of like a bundle kind of approach, where you don't just have one gradient, but you get some representation of maybe of a subdifferential or something like this. Anyway, so we are right on time. So thanks again, Stephen.
Yeah, thanks, Matthias. And
so more questions and interaction can be done in our Zulip chat. So you can open a new topic for that, and I'll be happy to chat more about CVXPY, and you can probably find a few pull requests to CVXPY soon. But now we move on to the next speaker. We have Julian Hall, who will tell us about HiGHS.
I'm going to share the whole screen. Okay. Awesome.
Okay, that works. Okay, yeah, so my great pleasure to introduce Julian Hall of University of Edinburgh, and we start right away. So HiGHS, the world's best open source linear optimization software, coming to SageMath, apparently.
Okay, thank you, Matthias, for inviting me to talk on this. I'm particularly interested because I've heard of Sage being mentioned by mathematicians in our school who are not in the optimization and OR group. So I realize it's used by all sorts of people. So it's a new source of potential source of users. So what is HiGHS? Is the first question, if you've not heard of it. Well, it's open source software for large scale sparse linear optimization, which is quite a long title. The name itself comes from the acronym, from the names of the original contributors, which is me, my recent finished PhD student Yvette Galabova, Huangfu Chi, and Lucas Schork, who will appear later. Also in the team now, we have Michael Feldmeyer and Leona Goswald. Specifically, HiGHS has got simplex and interior point solvers for linear programming problems. It's got a branch and cut solver for mixed integer problems and an active set solver for quadratic problems. It's all written in C++, but it's got interfaces to other languages and systems. The availability, it's very easily available. It's open source under the MIT license from GitHub, and it has no third-party code, so it's a simple, relatively simple build. And we have a website where you can find out more. And yeah, I think I've got reason to claim that it's now the world's best open source linear optimization software. So it's all based on solving LP problems, the most fundamental model in optimal decision making. And yes, there's two classical techniques and really only two practical techniques for general problems, simplex and interior point. Problems can have all different dimensions, but it's essential that sparsity in the constraint matrix coefficients are exploited. So here's a wee example. This is a problem where each pixel is a non-zero roughly, and it's got a kind of block diagonal structure and then a load of rows at the top linking it together. So problems can be sparse. It's worth exploiting the zeros, and they can also be structured. And sometimes we exploit structure. I've no idea what sort of audience I've got, so I'll give a little bit of math to show some of the interesting novel features that are in HiGHS. And I'm going to start with the primal simplex algorithm, just as a way really of establishing some notation, and hopefully it's something that's familiar to people. Where, yes, it's in the Tableau, you scan the cost row of the Tableau for a column to increase from 0. You then do a ratio test between the right-hand side and the column of the Tableau to find a variable to leave our basic set. And then we do interchange indices between the basic and non-basic sets and update the reduced right-hand side and the cost row. So if you've not seen that before, I'm not teaching it now, but it's probably familiar to some people. What's important, though, for the software is the data required. So in each iteration, you need the row of the Tableau and you need a column of the Tableau. And in the revised simplex method, that's obtained by solving linear systems of equations with a matrix B or its transpose and doing matrix vector products. That's the primal simplex algorithm. The dual simplex algorithm is almost identical in that there's very little that changes when I go from one slide to the next. The data requirement is identical. The updating is identical. The big difference is that you start with dual feasibility and you're looking for primal feasibility. And you first of all scan by rows and then by columns. So these two algorithms exist, and which one should you use if you have the choice? Well, the primal simplex algorithm is what's usually taught at undergraduate level. I refer to it as a traditional variant, but the issue with primal simplex is that if you add a constraint to a problem, so if you tighten a linear programming problem after you've solved it, and you're doing it in a sensible way, then you'll no longer be optimal, and in fact your previous optimal solution won't be feasible. The dual simplex algorithm is now the preferred variant. It's usually the default in most solvers. For various reasons, it's easier to get dual feasibility than primal feasibility. It's also possible to make more progress in many iterations than typically in primal simplex. And when you tighten a primal LP, you add a constraint to it, you relax the dual problem. So therefore, the optimal solution of the previous problem is still dual feasible. So you've got feasibility to start with. However, in practice, solvers need both for efficiency and robustness. Another kind of cool feature of simplex solvers, which again, if you're not in optimization, you might even find this interesting, because it all comes down to solving linear systems of equations, is first of all that the right-hand side of the system of equations is usually a sparse vector, because it's a column from the constraint matrix or a unit vector. And when the right-hand side is sparse, the solution is just a linear combination of a few columns of the inverse when you're solving Bx equals R. That's just linear algebra. And although B inverse we never form explicitly, it's quite interesting to look at its structure to understand how methods work and how to make them go faster. So if you look at a sparse matrix and think about solving Bx equals R, there's a matrix for an LP test problem. It's got about 10 non-zeros per column. And if you form its inverse, explicit inverse, then it's a dense matrix. And maybe that's not a surprise. If you take a random sparse matrix and form its inverse, then it's usually going to be full. It's got a reasonable number of non-zeros to start with. So therefore, if you solve a system of equations, even if your right-hand side is sparse, then the solution will have full density. But that's by no means always the case. Here's another LP problem, which is a bit larger. And if you form the explicit inverse of that, then it's about 0.5% dense. And so therefore, a small number of, when you combine a small number of columns of the inverse to solve a system, then you'll get very few non-zeros in the solution, which, since a general sparse matrix has a full inverse, is unusual. And you need to exploit that both when you are solving systems of equations and also when you've got the result. And in this case, the LP is said to be hypersparse. And there are huge performance gains from exploiting this in the simplex method. And it's quite it is quite incredible at times. You get problems with hundreds of thousands of variables where you solve a linear system and you've got like 10 non-zeros in the solution. So it can be as extreme as that, which for general non-linear system solver community is just bizarre, and they find it incredible. Right, so I'll give you a little bit more maths later as I tell the story of HiGHS and illustrating some of the stuff that's in it. We didn't always have HiGHS. I had a PhD student, Chi Huang Fu, who developed a parallel dual simplex solver, and we wrote up a couple of papers. And when he finished, he gave me the C++ code of this. Very, very smart guy. He went away to work for FICO and made their simplex solver the world's best. And after a brief break back in Edinburgh, he's been working for Cardinal Software ever since. And for the parallel solution of general LP problems, in a way, this is a kind of holy grail to try and parallelize the simplex method. Many, many, many people have tried. I've tried for donkey's years. And he, I think, has probably made as good a fist of it as anybody. And he took looked at dual simplex, and instead of doing standard dual simplex, he computed a few rows of the tableau, not the whole tableau. And that's the graphic here very much exaggerates what proportion of rows are computed. It might be 8 in 100,000. And if you've got a small collection of those rows, then there's a lot of parallelism in computing them. And then you do minor iterations of the dual standard simplex method just on those rows. And then when you've run out of iterations to do, you have to then kind of catch up on the global level, which requires an awful lot of independent system solves, which are task parallel. So basically, that produced speed up of between 2 and 4 on 8 processors, which isn't great for the parallel programming world, but it's pretty impressive for simplex. So that's in HiGHS. The other feature, it's not all simplex, is interior point methods. And the basis of interior point method is that you take the inequalities x greater than or equal to 0 and you replace them by negated log terms in the objective, so that you are just solving an inequality problem over a set of the solution of a set of equations, but minimizing now a non-linear function. And the essence of interior point methods is that you have to solve what's known as the augmented system, which is a matrix containing the constraint matrix twice and this magic matrix theta, which comes from interior points, which is diagonal. And that's a positive semi-definite system. And you need to be able to solve that efficiently if you want to implement interior point fit well. And Lucas Schork did a PhD with Jacek Gonjo in Edinburgh, and he took a very different approach. Most people use Cholesky decomposition on the augmented system, whereas he used iterative techniques, which needed very, very careful and clever preconditioning for general problems. And he used preconditioned conjugate gradient with a preconditioner derived from a kind of simplex-like basis. Details I won't try and go into. But basically, when he'd finished, he then bequeathed the C++ code of his solver IPX to us, and he's been working for Cardinal alongside Chi for the last couple of years. So HiGHS as a project, well, we created the name in 2018, and we put in, first of all, and based it on the simplex solvers. Then we integrated the interior point solver, and then since towards the end of 2020, Leona Gottwald has been writing a MIP solver and improving our LP and MIP pre-solve. And a PhD student of mine, Michael Feldmeyer, has written a dual active set solver for quadratic programming problems. In terms of users, well, we have many, many anonymous users, which is always the curse of open source software, when you need to be able to say what users you've got. But a couple of prominent users are SciPy, as briefly mentioned by Matthias. They adopted HiGHS as their premium LP solver in 2020, and SciPy 1.9, which I don't know when it's coming out, but it will have MIP capability through HiGHS. That's all good to go, I believe. And in other interfaces, the JUMP optimization and modeling system, HiGHS has become the default MIP solver in their documentation. In terms of performance, why do we think it's so good? Well, these are based on independent benchmarks that the industry uses, put together by Hans Mittelmann. And he compares closed source and open source solvers. And these are the current results. He solves 56 LPs with a time limit of 15,000 seconds on each. And there's really two measures. First, fairly obviously, is speed. And he takes some fancy geometric mean of speed, of solution time, and then normalizes it. So the fastest solver is COPT, which is written by Cardinal, which is where Chi works. After that, there's one solver produced by Alibaba, which is well known in China, which is a bit slower. And then you've got a solver from Gurobi. There's a solver from Huawei, which has got an asterisk because not all of the problems were tried, and it should be a lot faster than that. Then you've got CLP, which is the John Forrest simplex solver. Then you've got HiGHS, then you've got MOSEC. The other measure of how good things are is how many of these problems are solved. And you can see that COPT solves them all, and so does Gurobi. And we solve a decent number of them. Then you've got 4 other solvers for context. You've got Google's simplex solver GLOP, which is considerably slower than ours. And then you've got Zoplex, which is the LP solver from the ZIB, Berlin, MATLAB's solver, and GLPK, which is very popular, but is very poor. So the three Chinese solvers dominate the benchmarks, and that's for all sorts of reasons. And I think it's a bit of showing off. There's all sorts of clever tricks, which are nothing really to do with simplex, that allow you to solve these problems fast. Cplex and Express are not in the Mittelman benchmarks. They haven't been for a few years due to a bit of a dispute. And HiGHS results are now better because Hans has added 16 blind problems. So these are not problems which are publicly available, and so therefore people can't train their solvers quite so well. So that's simplex. Interior point, oops, sorry, and HiGHS will get better. We're not so worried about simplex performance at the moment. For interior point, again, 49 LPs, not quite the same set, slightly harder because interior point's better for single LPs. And with a time limit of 15,000 seconds, COPT is the best, and that's where Lucas Short works. Then you've got Gurobi, and then Alibaba. And Mosaic has more of a focus on interior point. Nitro is another commercial solver. And then you've got Google's brand new solver. This is new as of about a week ago in Mittelman's benchmarks. This is Miles Lubin's first order methods code, Miles and a few people, which is pretty fast, but doesn't solve quite so many problems as we do. And then you've got slower solvers. The feature of Google's code is that and a couple of others, is that it doesn't have crossover. So interior point just finds an optimal solution, but it's not a vertex solution. You need to do something known as crossover to get a vertex solution, which is important for a lot of applications. And some interior point solvers don't have this because the crossover is actually quite a hard thing to get right, particularly if you use Cholesky-based techniques. And we're looking still to improve our interior point solver because it's getting a lot of attention in the energy systems world at the moment. The mixed integer solver, well, Leona Gottwald wrote it from scratch, and it's benchmarked on 240 problems. It's a classic test set with only 2,000 seconds per problem. And when we started off, well, the best solver is Gurobi's. And I put GLPK in there for reference. It only solves 23 of the 240 problems, and it's 55 times slower than Gurobi. And fairly soon we were considerably better than GLPK. Months later, then we had CBC in our site. CBC is John Forrest's integer programming solver, which is very popular. It's been a great solver for many years, but fairly soon we were better than CBC and had Skip in our sites after a month. And by September, we caught up with Skip. And by February of this year, we are well clear of Skip, and we now have some of the lesser commercial solvers in our sites. And there's still much scope for further improvement in HiGHS. In particular, HiGHS is still only single-threaded, and things like Skip and COPT and Gurobi, of course, are all multi-threaded, multi-core solvers. And we'll be introducing multi-core in the coming months. So that's the performance. The solvers have been out for a while, people are using them, and now that we've got to this elevated position in the world, the School of Maths has recognized this is rather a good thing to have, so therefore it's funding, or underwriting, I should say, Yvette and Leona to carry on working on the stuff that they do. Yvette does all the software engineering and dealing with interfaces, and Leona's just left to get on with the MIP solver. We're looking to increase the presence of HiGHS. There are current projects to get it into Octave and Pyomo. Pyomo are very keen that HiGHS should be available from their systems, so they're helping us. We have an agreement that we're going to put it into Google's OR tools. And we're looking to improve performance. We're looking to overtake CLP to be the best open source simplex. We're looking to develop a Cholesky-based interior point solver for the problems where the iterative solver isn't so good. And like I say, catch up with some of the lesser commercial MIP solvers. In the longer term, we want to expand the team and develop new solvers. Since we've got an active set solver for QP and we're going to get interior point for convex QP, it's sensible to get into NLP. And also, since we've got such a powerful MIP solver, MinLP, but we may also get into conic optimization. And we're also looking to offer more services like support services and consultancy. So, HiGHS coming to SageMath. What's on the agenda? Well, I've had a look at what's currently in SageMath for linear optimization. I see that you've got CVC, which means that you're using CLP for LPs and interior point via that route. You've got GLPK for MIP. You've seen how good that is. And you've also got CVXOpt, which is an interior point solver I don't know much about for convex LP and QP, and presumably an LP. And if people have got Cplex and Gurobi licenses, you can use that. So why add HiGHS? Well, there's better performance than CVC, and there's vastly better performance than GLPK. And one difference about HiGHS is that it's fully supported, whereas some of these open source solvers, which are very, very popular, like CLP, CVC, GLPK, and LUsolve, I'm not sure quite how well supported they are. There's a community that uses them, but HiGHS is fully supported into the future by real people who are employed. And also there's the prospect of just bespoke features that you wouldn't get out of a commercial solve. What HiGHS can't do, and I realized that I was potentially getting a proper maths audience when somebody emailed me saying, well, I need to be able to solve QPs in exact arithmetic, and will HiGHS be able to do this? And the short answer is no. HiGHS really is for large scale problems, and exact arithmetic's prohibitively expensive in large scale. And the other thing it won't be able to do is guarantee solutions. There's no sort of provably correct algorithm which is guaranteed to work. As you've seen from the test problems, it's pretty robust. It solves lots of hard problems, but there's absolutely no guarantee that we will find a solution if one exists. So, but the LP solver is pretty robust, since gazillions of LPs are solved when you solve a MIP. How can we integrate HiGHS into SageMath? Well, I had a look at this and I explored some SageMath tickets, and it's been suggested that SciPy is used as an interface to HiGHS, which is perhaps quite elegant, but the problem is that the SciPy interface to HiGHS is very limited. It really is just, you've got an LP to solve, or in future a MIP to solve. Well, this call will solve it and return the answer. But which is what all that many people need. But if you're really wanting to use the full power of HiGHS, you're going to want to build models, you're going to want to modify models and resolve efficiently. And none of that's possible through SciPy, nor do I ever think it will be. So an alternative is there's a thin Python wrapper around the C++ class of HiGHS, which is being developed in collaboration with one of the people from Pyomo, because they want it. And that, I think, is just waiting for HiGHS to be for it to be possible to pip install HiGHS. And we're working on that, and we're getting near it. and it works on some architectures, but not all. So that's fairly close to being ready. And that will give full functionality of the C++ class through Python. So all the things that I've heard people wanting to use and bespoke things could be built in. But it needs approach from both sides, because there's an awful lot of SageMath stuff which we wouldn't have a clue how to start working on. And so therefore, hopefully some SageMath developer will be keen enough to work with us to make it happen as well. And so that's it. HiGHS there is your high performance LP solvers for both classical techniques. It's a very high performance MIP solver. It's probably the best of our solvers, and a QP solver. You can call it for any language, including Python, or most major languages anyway. There's application interfaces from Jump, and Pulp, and SciPy, and we're going to add, we'll be adding to those in the future. It's a very permissive license, so you don't have to worry about that in any way. There's no third-party code, so it makes the build much easier, and it's available to the world, and hopefully coming to SageMath. Thank you.
Thanks very much. These are very impressive achievements, and yeah, so the SageMath community is looking forward to collaborate. But we've got plenty of time for questions and comments, so I'll open the floor for.
Perhaps I can comment. Do you hear me?
Yes, Dima.
Yeah, I just wanted to comment that actually Sage has an arbitrary precision LP solver, PPL, which was not mentioned in the talks. It's there. So this is our golden standard in a sense that if you have a very badly conditioned LP, you can still hope to solve it using this solver, and in our applications actually might be crucial.
Okay, apologies. I didn't. Sorry, shall I stop sharing my screen?
Yeah, so PPL is a kind of for the opposite of large-scale applications. It's
yes.
What one. I mean, it does provide exact rational LP, but it is not a revised simplex method. It's a very basic solver, and of course, yeah, for Sage. So exactness and certified computation is very important, and so that's for example, Julian, why I asked for what the status of like detailed interfaces to like the Tableau and so on are, because if one is lucky, one can of course extract the combinatorial information from optimal numerical solution, and then if one is really lucky, one can just reconstruct the optimality certificates, and in this way get a certified optimal solution.
Okay.
If one is not so lucky, one can try a hybrid method, trying to resolve either using iterative refinement schemes, or crossing over to an exact rational simplex, and again in the hope that there are just a few cleanup iterations necessary in exact arithmetic, something like this. Basically on the Sage side, there would be the at least some infrastructure for doing kind of laundering schemes of that kind, as where we run the fast numerical solver and then extract information that we can use to later on refine things and bring things to the exact and certified computation side.
It might be interesting if your problem was any real size and you've got cleanups to do with exact arithmetic, it would take you far longer to do those than solve the problem with floating point arithmetic, I'm sure. It's just it's horses for courses, as we say. It's just HiGHS is just not for that. And maybe we can, maybe there's some sort of useful combination could be put together, but I would have to see.
I mean, the zip people have made some progress in this direction. I believe they had this exact version of skip, also based on an exact version of Soplex, less so using rational arithmetic, but rather using like iterative refinement methods, also taking differencing with the last solution, and then basically scaling tricks of that sort to some extent. But of course, there are, for example, problems in which I think Dima, you were interested in those problems where like the basis is so poorly conditioned that one basically needs to deal with that already in high precision rather than in like standard double precision. And so I think there are various problems out there, but like for medium-sized problems where one is lucky enough that one can just launder a numerical optimal solution to exact certified solution where you just recompute the certificate and then lucky enough.
I should say that we're looking at another thing we'll be doing is putting in quad precision, which can make a big difference on ill-conditioned problems. I know it's not an answer to everything, but the experience we've done, it's clear how much more clarity you get when you do that. And of course, all the commercial solvers will switch to quad precision if necessary.
Julian?
Yes, I have a question for Julian. So you have provided a nice survey of the best servers on the market, and I was wondering, for exact arithmetic, are there any nice solvers on the market, rational arithmetic, or in the spirit of hybrid method? So you get the basis and do the last few steps in rational arithmetic. Are there any good method or good solver?
Well, thank you. I'll be honest. I mean, I knew about the Soplex and Skip work on exact solving with exact to get exact solutions, and that is probably your best bet as far as I know. It's just not a world that I inhabit, and when it comes when it comes to the benchmarking, all the benchmarking is being done on problems which are far too large for any exact arithmetic solver to even think of solving. So therefore, any solvers are not on the benchmarks. Yeah. So yeah, apart from the stuff done at the Zuse Institute, I can't recommend anything.
Thank you.
More questions and comments?
I guess I was curious, were those timings that you showed or the benchmarking that you showed, was that single threaded or were some of those multi-threaded?
Every solver is given, I think, 8 or 16 threads to use. Oh, okay. So if it can use them, it uses them. If it's a single threaded code, then it will only use one of them. There's very little multi-threading in Simplex. I mean, Express is about the only commercial solver with multi-threading for Simplex. And for interior point, yeah, Gurobi will be multi-threaded interior point, which will give it an advantage. And everybody's, apart from us, is multi-threaded for MIP. The GLPK results are single-threaded, but that's clearly just a single-threaded code for MIP. And it's, yeah, so yeah, it's it's multi-threaded when you if you can handle it is the answer.
Got it.
More comments, questions? So I have lots of questions and comments. So there's no obligation to the audience to listen to me, but so we've got quite a bit of time before the next talk starts. The next talk starts on the full hour. So I'll just keep rambling, and nobody needs to feel the obligation to stay online. Yeah, so I have some, I guess, questions, maybe requests or wild dreams about the MIP, let's say branch and cut solver that is being developed in HiGHS. So measure the traditional model in providing a general purpose branch and cut solver is that there's a loop that's under control of the solver, so kind of more or less opaque implementation, and then if you're lucky, there's some useful callbacks provided. So in the olden days with Cplex, one had pretty good control over node selection and doing local cuts and so on, and but kind of the solver kind of dictated the overall control flow, and so other people who got like training in semantics of programming languages and so on. Of course, there's the obvious dream that one should be able to interact with such a such a solver in a more fine-grained way, so that the control flow is more customizable. So do you have any plans to make kind of the branch and cut available as let's say in a coroutine like fashion? I mean, so C++ 20 has support for coroutines, and there are advanced control flow structures of this kind, and so that's probably also the perspective of the threading. Yeah, so would it be possible that we on the side of the user, one has an idea of how time should be spent, how the branch and cut solver should try to find more more feasible solutions, or find a better bounds and so on, so that like the user can kind of drive the behavior of the solver. Basically, the user can basically decide how time and computational cores are spent, because there are other things. Yeah, so there are other parts of the algorithm that are not under the control of the solver that should also be run. Yeah, so MIP solving only being part of an overall algorithm. Some thoughts on this?
Yeah, well, we've certainly, of the features that people want of MIP solvers, the two immediate features are callbacks so that people can add cuts, sure. And there's 3 standard callbacks, and Leona's in the middle of implementing those. 2 of them are trivial to implement. The other one I think is taking more time. And then there's also this idea of collecting pools of solutions, which is valued by people who are solving MINLPs, because they don't necessarily, they want a collection of solutions, not just one. Some of the other ideas you're suggesting, I've not put them. I can discuss it with Leona. I think there's a bit of there's probably a bit of a conflict between having a very, very efficient MIP solver and having something which is customizable by a user in terms of where the effort goes. And yes, a very, very expert user might be able to get some improved performance out of it. But not many, I would think, when you get to very high levels of sophistication like ours. So I suspect that's a bit of a long way off. We spoke some time ago to Ted Ralphs about highs when we said we were producing the MIP solver, and he was quite, and I think he's right, he's saying, well, it's a shame if it's just a black box, because people are wanting to play with stuff, and having a good MIP solver to play with and be able to experiment with is important for the world, the academic world at least. And some of the things he was talking about, we will be able to allow people to do, but it's not been a priority at the moment. It's getting performance up really was the initial priority.
I mean, so in more recent years, also when CPLEX introduced, for example, dynamic search, kind of use of callbacks became kind of less useful, for example, right? So basically, as soon as a user put in callbacks for cut or node selection, it would turn off dynamic search, giving you immediate performance degradation, and you would have to work hard to even just go back to the baseline.
I can think that's the sort of thing that can happen.
And so I guess a lot of users in the practice are basically not using callbacks, right? Are using things just in a very black box-ish kind of way, updating models and then resolving like augmented models from scratch. So without any kind of warm start, and maybe imputing some known solutions, and maybe putting in some some dual bounds or something like this. But so I think there's a huge potential in having a kind of more flexible API that goes beyond excuse me, that goes beyond what kind of the traditional model of like the solver controlled branch and cut search with then possibilities for callbacks would offer. So that it becomes a kind of more composable, that you can you have the state of the solver, and you can say, okay, let me try to make progress toward producing more solutions for the next 200 time minutes, and then I can do some other stuff that is application specific and so on. So I think there would be a lot of value in kind of opening up this kind of black box plus callback paradigm, in particular in view of control flow in a single threaded setting, and also a multi-threaded operation. I mean, so suppose I have 16 cores. But there's application logic that can do some stuff. Maybe you have some heuristic search that can run, but on the other hand, you can invest into doing more general MIP stuff and on some other cores and so on. So I think there would be a lot of value in having like a clean, more flexible way of driving this, other than the kind of 1990s style loop and callback kind of paradigm.
Okay, I mean, my problem talking about this is that I'm a continuous optimizer. Obviously, I've had an awful lot to do to get the simplex solver to talk efficiently with the MIP solver, but a lot of the MIP techniques are just closed book to me. I'll chat with Leona to see where we can take it from here in terms of opening it up a bit. Yeah, sure.
Yeah, so the work that Leona did on Papilo, this exact preprocessor and presolver for MIP, is basically all of that functionality. Is this going to be available out of the box in HiGHS at some point?
No. Well, yes and no. I mean, there is not a line of Papilo in HiGHS. Let's make that clear. Which is important from the point of view of licensing. Clearly, she knows how Papilo works because she wrote it,
yes.
Most of it anyway. I don't know. I mean, the pre-solve is good enough for single-threaded at the moment. We've yet to talk about what else she might do in pre-solve. And there may be ideas that are in Papilo that can get used in HiGHS, but we've not talked about that yet.
Yeah, so Papilo also works in exact arithmetic. Yeah, so I think this is a very good match for Sage, because basically it can do a problem transformation, right?
Yes.
So the pre-processing that is exact and certified, and so probably that's something that independent of the HiGHS backend is probably of value for Sage, because we can have a exact arithmetic problem transformation to that maybe enables it to run various solvers on kind of poorly presented problems.
Yes, our pre-solve can be run on its own, and I know that Papilo was going to have exact pre-solve because, and I don't know whether that can be incorporated into HiGHS, how readily. Again, I need to talk to Leona if that's going to be useful for people.
Okay, so are there more questions from the audience? Comments? If not immediately, there's always the chat, so out there on our Zulip. So thanks again, Julian.
A pleasure. Thank you.
Direct talk. And we will take here a 24-minute break until the scheduled next talk starts. The next talk will be by Nina Miolane on Geomstats, Python package for differential geometry in statistics and machine learning. So then, nice to meet you.
Yeah,
thanks
nice
for
to meet you.
joining us here.
Yeah, thank you for the invitation. I'm excited.
Okay, so I think we can slowly start. So it is my pleasure to introduce Nina Miolane, who is going to speak about Geomstats. Please.
Thank you, Matthias, and also thank you very much for the invitation. I'm delighted to have the opportunity to present the Geomstats today. And Geomstats is a Python package for differential geometry and statistics and machine learning. Before I talk more about this package and present it from a user's perspective and from a contributor's perspective, let me give you some information of why we created Geomstats and how it started. So Geomstats actually started in the biomedical imaging community, where we were interested in quantifying the shapes of biological structures. So biomedical research in general is interested in understanding the fundamental mechanisms of life, with the hope that this can lead to better diagnosis and better treatments of different diseases. And today,
in biomedical research, we are actually very lucky because in order to understand these fundamental mechanisms of life, we can look at them. So we can directly observe these biological structures through different types of imaging modalities. By the way, by biological structures, I mean organs at the macroscopic scale, and then all the way down to the nanoscopic scale, I'm going to mean tissues, cells, organelles, or molecules. And so in biomedical research, we can observe these biological structures through different imaging modalities. At the macroscopic scale, to look at organ shapes, we have magnetic resonance imaging. And all the way down to the nanoscopic scale, we have, for example, cryo-electron microscopy. And the point I want to make with this introduction is that across all of these images of biological structures, there is one feature that we are really interested in, and this feature is the shape of the biological structures. And this is because there is this fundamental biological assumption that states that biological shapes are linked to physiological functions. And therefore, there is a lot of biologically and medically relevant information to be extracted from the shapes of biological structures. Let me give you a few examples, all about the shapes of Alzheimer's disease. At the macroscopic scale, Alzheimer's disease is characterized by shape changes of the brain that you can see in this simulation of a 3D brain that is undergoing an atrophy of the brain matter. So you can see, for example, at the center of this brain, the ventricle growing larger and larger. So at the macroscopic scale, Alzheimer's disease is correlated with organ shape changes. Now, at the microscopic scale, Alzheimer's disease is also correlated with shape changes, but this time it's changes in the shape of cells and specifically neurons. So the atrophy that you saw at the macroscopic scale on the brain shape changes actually comes from the death of neurons. And you have on this video a neuron dying and retracting the axons and dendrites. So at the microscopic scale too, Alzheimer's disease is correlated with shape changes. And actually all the way down to the nanoscopic scale, Alzheimer's disease is what's called a double prion disease, which means that there are two proteins, beta amyloid and tau, that are going to change shape and therefore aggregate inside the neurons, but also outside the neurons. And this is what leads to the death of the neurons that we were just visualizing. So it's interesting to see that across the macroscopic, microscopic, and nanoscopic scale, Alzheimer's disease is characterized by shape changes. So we have established that the healthy of the pathological state of a biological structure or the function of a biological structure can lead to different shapes of this biological structure. What our work in biomedical research was interesting in doing is inverting that model. So whereas the biophysics tells us what a healthy state generates in terms of biological shapes, our work is interested in performing what we call geometric learning, meaning we go from the shapes as we observe them in medical images or biological images and inverse this to get biomedical insights. And this is in this context, the bottom line of this slide, that Geomstats was created. It was created with the purpose of performing geometric learning, so statistics and machine learning on shapes, specifically biological and anatomical shapes, in order to lead to biomedical insights. So this was an introduction of the birth of Geomstat, which was created in 2018. And we could call it a Python package for geometric learning. That started for geometric learning on shapes, and is now extended to geometric learning for any type of data that live on manifolds. This is the outline of the talk for today. So I'm going to motivate a little bit how shape data belong to manifolds. in the first part, so introducing a few models of shape data on manifolds. In a second part, I'm going to present Geomstats, an open source software in Python for geometric learning, and give a little bit more context about its objectives, and introduce it from a user perspective and from a contributor perspective. And then at the end, I'll showcase an example, a use case of Geomstats to perform geometric learning for shape analysis in the context of shape analysis of cells, which is what you see on the bottom left, the cell shape. Starting with part 1, models of shape data on manifolds. So I'm going to introduce 2 models of shapes and shape transformations. There are others, but I'm going to introduce the 2 main ones, at least the main ones in our works. So first of all, we see on the left of this slide, you can consider a shape as an equivalence class. And specifically, you describe the shape of an object, such as the shape of this closed curve, which it's actually the boundary of a cancer cell. You can represent the shape of this object, this closed curve, as everything that remains invariant when we remove translation, rotation, scaling, and potentially reparametrization of the sampling, like resampling of the points that discretize this curve. So again, the shape of an object is everything that remains invariant by translation, rotation, scaling, and possibly reparametrization. If we want to abstract that a little bit, we're going to say that the shape corresponds to the orbits of the action of a Lie group on the object. So now we write G0, the Lie group of translation, rotations, scalings, and possibly reparametrization. It's the set of all these elements, and from a mathematical perspective, it forms a Lie group. Each element of the group can act on the object as shown by the illustration. And now the shape is defined as the orbit of the action of this group on the space of objects. So by this, we define the shapes as the elements of a quotient space, Q, whose equation is given at the bottom. So the quotient space, which is the space of shapes, is defined as the equivalence classes written as bracket of X for X belonging to another space, let's call it M. And I write the equation of this equivalence class, bracket of X, the equivalence class of X, so the shape of the object X, which correspond to all the points in the original space M of objects that can be reached by a transformation, G0, that could be a translation, rotation, scaling, of reparametrization of X. We see that Y equal G0 of acting on X. So that's the first model of shapes. Shape space, the shape space is what we call the quotient space generated by the action of a Lie group. The second model of shape that I'm introducing today is representing a shape as a deformation. So for this model of shape, we assume that the template shape is fixed. So typically this peanut-looking shape is fixed and is called a template. And now any other shape is represented by a smooth deformation from this template. This smooth deformation is what is illustrated in this video. So again, we have a notion of action on the closed curve or the object, but now it's not the action of a translation, rotation, scaling, of reparametrization. Rather, it's the action of a deformation, a smooth deformation. So we call the set of all possible smooth deformation G. From a mathematical perspective, it's again a Lie group, but it's not the Lie group of translation, rotation, scalings, and reparametrization. It's the Lie group of smooth deformation from a template. And now, instead of quotienting out, of removing the action of this Lie group, as we were doing for the translation, rotation, scaling, we wanted to remove these ones because they do not change the shape. in the case of what's on the right of this slide, we want to keep this Lie group because this deformation is what represents the shape. The shape is represented by the deformation from the template. And so in that case, we keep the Lie group. And actually the Lie group itself is the shape space. So the shape is represented by a deformation from a template. Ooh. Show the video again. Oh. Is represented by a deformation from a template, and therefore as an element of the Lie group of deformations. So here on the slide, you have two models of shapes and shape spaces. And these two models have something in common. In both cases, the shapes are represented as elements of manifolds with additional geometric structure. So on the left, the model of shape space as a quotient space is a model of manifolds. And on the right, the model of shape space as a Lie group is a model of manifold. A Lie group is a manifold with a group structure. So we have established that shape spaces are manifolds. To define a manifold, I'm not going to give the mathematical definition. I'm just going to give an intuitive definition. What we call manifolds in this presentation is a nonlinear generalization of a vector space that locally looks like a vector space. So for example, the sphere that you see on the screen is a manifold because it's nonlinear. The surface of the sphere is curved. But if you look closer in the neighborhood next to a point of the sphere is going to look flat. In the same way that we live on the surface of the Earth is curved, but locally the Earth looks flat to us. So that will be the definition of manifolds that we use in this presentation. So we said that shape spaces are either quotient spaces or Lie groups. In both cases, they are manifolds that are nonlinear generalization of Euclidean spaces. On the screen, you have an example of one of my favorite shape spaces because it's usually easy to visualize. You can see the shape space of triangles. So the shape space of triangles is this 2D sphere where I have superimposed triangles to indicate which point on the sphere corresponds to which triangle. And you can see superimposed in blue a geodesic in the surface of this sphere, which is a trajectory in the space of triangles. So this is a low dimensional example, 2D triangles, meaning 3 points in 2D, the shape of 3 points in 2D. The shape space of the 2D triangles is a sphere, but even in higher dimensions, shape spaces are manifolds. And for example, the shape spaces of curves and surfaces also use hyperspheres. They're not exactly hyperspheres, but they use hyperspheres. So since shape spaces are manifolds, our data that are biological shapes are points sampled on these manifolds. And now we are interested in doing statistics, machine learning, or deep learning on biological shapes to get biomedical insights from the information in these shapes. And therefore, we are interested in doing statistics and learning for data that are sampled on manifolds. What are the type of statistics and deep learning that we'll be interested in doing? And why do we need to generalize statistics and deep learning to data on manifolds? So let's take the shape space of triangles, the sphere. I've just removed the triangles. Imagine you have 2 points sampled on the sphere, so the 2 blue points. Each of them represents a shape that is a triangle. If we were to apply traditional statistics, and so if we want to do statistics and, for example, compute the mean, the average, which is arguably the most important statistical information that we may want to extract from data. So assume we want to compute the mean shape of these 2 triangles represented by these 2 blue points. If we use traditional statistics, we're gonna compute the mean as the weighted sum of the two blue points, the linear mean, it's a linear expression, and we will get the orange point that is inside the sphere. And so we see that in this case, the mean of 2 points on a manifold, on the sphere, does not belong to the manifold. And what that means is that the mean of 2 triangles will not be represented as a triangle. So I'm trying to do the mean of shapes, and the result is not even a shape. So traditional statistics do not apply to this case. What we want to do instead, and what is implemented in Geomstats, is something like what you see on the screen, where we join the 2 points, so the 2 blue points representing the triangles, by a geodesic and take the middle of this, which is going to be the orange point, which is now on the sphere and is therefore a triangle. This point is going to be this orange point, or the result of this computation is going to be called the Fréchet mean. Now you may ask why we don't do linear statistics, so compute this orange linear mean, and then project it back to the manifold. Because in this case, instead of having to generalize statistics, machine learning, and deep learning to data on manifolds, we'd rather only have to compute a projection operation, and then we just have to compute all the linear operations as usual and just project them back on the manifold. Now, there are problems with this approach, and 2 main problems. The first one is that by doing so, we adopt what's called an extrinsic approach. And this extrinsic approach requires more dimensions, so more memory requirements and more computational power than the intrinsic dimension. So if you think about this sphere example, computing the linear mean, so the orange point, in the ambient space of the sphere, which is the 3D Euclidean space, requires 3 dimensions. 3 dimensions of the 3D Euclidean space. Whereas if we stay intrinsic, we only require 2 dimensions because we perform all the computation on the sphere, and therefore potentially yielding better memory and computational requirement. That's the first reason. The second reason is that computing directly on the sphere may lead to a better intuition. If you think of the sphere as the Earth, for example, points on the Earth are more intuitively represented by their longitudinal and latitudinal, by their longitudes and latitudes coordinates, which are more intuitive than if they were represented by XYZ. And maybe another argument in favor of staying on the sphere and performing all of the computations on the sphere rather than performing computation in the 3D Euclidean space and projecting that is that even though this sphere is easily embedded in 3D Euclidean space, and even though there is a theorem that states that all manifolds can be embedded in a larger maximum dimension 2M Euclidean space, this embedding is not necessarily constructible. We cannot necessarily implement this embedding. And therefore, this strategy of performing operation in the larger space and projecting it doesn't apply. So hopefully I convinced you that there is a need of generalizing statistics, machine learning, and deep learning to data on manifolds, and specifically for these shape spaces. Which leads us to the second section of this talk, which is about Geomstats. So an open source software that generalizes statistics, machine learning, and deep learning to manifolds. So Geomstats is available on PyPy, on Conda 2 recently. And its documentation is available on geomstats.ai. And it has 3 main objectives. The first one was to teach hands-on geometric learning. The second one, the first one is to teach hands-on geometric learning. The second one is to support research in geometric learning. And the third one is to democratize the use of geometric learning. So in terms of teaching hands-on geometric learning, I personally learned differential geometry in my general relativity classes in master, and I read a lot of excellent books about it. But very often these books didn't provide an implementation of the concepts. They were not included in the textbooks, and I discovered open source implementations later on. What Geomstats can do, and I'm sure other software can do it too, is to allow to develop a curriculum in machine learning and data science that introduces concepts of differential geometry in a hands-on approach. So on the right, you can see something from one of my own class on biological shape analysis, where I use Jupyter notebooks to introduce concepts of differential geometry together with code that I can run interactively during the class and that the students can run on their versions of my notebook later at home. So for example, if I want to prove that a hypersphere, or let's say the sphere, is a manifold that can be described as a level set and therefore with what we call a submersion, I can use Geomstats and run code from Geomstat to exemplify this fact. And the students can play with it to understand the concepts better. That's the first objective of Geomstats, to teach these abstract mathematics to machine learning students in a hands-on fashion. The second objective is to support research in geometric learning. So this research is typically produced by mathematicians, applied mathematicians, and these researchers can bring their code into Geomstats, and we're going to cite their different methods. And so we provide a platform for this research to be open source there and available to the wider community. The last one is the democratization of the use of geometric learning. So this one is typically geared towards engineers or scientists from different applied disciplines that do not necessarily have a background in mathematics, but can still use Geomstats and the geometric learning methods available in it, as long as they have some understanding of traditional machine learning, such as scikit-learn, for example. So let me show you how this goes. This is related to the typical use case of Geomstats, which is what's in that blue box here. Let's say we want to compute the mean of two points on the sphere, which is what I had on the slide a little bit earlier. Or we want to perform any type of learning algorithm on a manifold, and we do not have background in differential geometry. The typical use case goes as follows: 2 steps. First, geometry related. Second, statistics or learning related. First, we instantiate the manifold of interest. So this requires an understanding of which manifold we have, to which manifolds our data points belong. In this case, we say we instantiate a sphere as an object of the class hypersphere with input parameter dimension equal to. First step 1 focuses on the geometry. Second step focuses on the learning. And that's where an understanding of scikit-learn is important or interesting, because it's going to work the exact same way as your traditional scikit-learn algorithm. So first, in the second step, you instantiate your estimator or your learning algorithm. Here, I will instantiate the Fréchet mean, which is the generalization of the mean for manifold. Observe that the only parameter that it needs is what we call a metric. So in that case, I use the metric of the sphere, sphere.metric. I've instantiated the estimator or the learning algorithm of interest, and then I can fit it to points, assuming I have my 2 points that have been sampled on the sphere. And then the estimate of the Fréchet mean will be stored in this estimator object, and I can get it. So this is the typical use case of Geomstat that exemplifies how it can democratize methods of geometric learning that may rely on abstract differential geometry, but the technicalities are hidden behind a scikit-learn inspired API. So even though mathematicians, applied mathematicians can contribute code to the core module of Geomstats, the users on their end do not require a specific understanding of differential geometry. Now let me comment on the modules that Geomstat has available, which is on the top of the screen. So the two main modules are geometry and learning. Geometry stands for differential geometry, which includes pseudo-Riemannian or Riemannian geometry. And the second main module is learning. So all the learning algorithm built following a scikit-learn inspired architecture. We have a new module called information geometry. I won't comment on that in this talk, but happy to take questions. Then we have a datasets module to provide open source real-world datasets for data that belong to manifolds so that users can use our techniques and the datasets are readily available, and a visualization module too. And lastly, let me mention that we have 4 backends available. So Geomstat can be seamlessly used with NumPy, TensorFlow, Torch, or AutoGrad, with Jax backend coming up with the same code. So we develop a GS dot coding, where GS stands for Geomstats. And you're using this GS dot syntax, you can transform your code to be run as NumPy, TensorFlow, Torch, or AutoGrad code. There are libraries that are very related to what we do. I'm just mentioning the ones I know and that are in Python. About the first 3, PyManUp, GeoOpt, and MyTorch, as some of their names suggest, with the opt, they are related to optimization on manifolds. So we want to optimize a parameter that belongs to a manifold. By contrast, our data belong to manifolds, not the parameters of the statistical model describing the data. The data themselves belong to manifold in the use cases that Geomstat is interested in tackling. Then you have PyTorch geometric, Theano geometry, and Jax geometry. PyTorch geometric focuses on statistics and deep learning on graphs, not on points that belong to any manifold, specifically on graphs. Theano geometry and Jax geometry are the same package in 2 different backends, also interested in studying shapes, and also providing an additional module for stochastics on manifolds, but not as maintained as Geomstats, for example. Then we have PyRiemann, Miolane, PyQuaternion, H2 surface match, and SRNF match code, which are libraries that allow us to do statistics and learning for data on specific manifolds. So 6 and 7 here are dedicated to data that live on the manifold of SPD matrices, symmetric positive definite matrices. PyQuaternion points on the manifold of 3D rotations. And 9 and 10 points that are surfaces, so on the manifold of surface shapes. In contrast, Geomstat is coded so that all of the learning techniques that are coded in the learning module can be applied to any manifold coded in the geometry module. So there is a 2-way table, if you wish. Any algorithm, almost any algorithm can be applied to almost any manifold. And last but not least, SageMath, which incorporated the Sage manifold code, has an extraordinary contribution in terms of differential geometry, and I think inspired by needs in the field of general relativity, but not as much statistics and learning. So let me present now Geomstats from a user's perspective and from a contributor's perspective. But from a user's perspective, which is the easier one first, we want to generalize statistics and machine learning to manifolds. Statistics and machine learning already exists for data on the vector spaces. How do we generalize this? Well, we can deconstruct all the statistics and all the machine learning algorithm so as to extract the elementary operations, the elementary building blocks, and then translate these elementary building blocks to their manifold version. So what are the basic building blocks of any algorithm on a vector space? Well, first, we need to be able to talk about the points on a vector space or vectors. Very often, we need a notion of inner product on the vector space, making it a Euclidean space, if you take a Euclidean metric, or notion of distance. Very often, we talk about straight lines. Think about linear regression, for example, we need a line. And very often we talk about addition and subtraction, adding a vector like this black vector to a point like this blue point to get another point, or subtraction, subtracting 2 points, the 2 blue points to get the black vector. And if you look at most of statistics and machine learning, they're all written in terms of these building blocks. So naively, or at least in the first try, if we are able to generalize these operations, that we are able to generalize statistics and machine learning. And that's everything that the users need to know. They need to know that translation to have some understanding of what's going on in geometric statistics and geometric learning. So points and vectors that were on the vector space are generalized to points on the manifold, such as the sphere that you can see on the bottom right, and now tangent vectors. The notion of inner product that we can put on a vector space becomes a metric, a Riemannian or pseudo-Riemannian metric, which is a collection of inner products at each of the tangent spaces at each of the points of the manifold. The notion of distance between 2 points, such as the 2 blue points that you can see on the top right, becomes a notion of geodesic distance. That will be the length of the black curve between the blue and the orange point that you see on the bottom right. The generalization of a straight line on the manifold becomes what we call a geodesic or autoparallel curve on the manifold. Adding a vector to a point on a vector space becomes adding a tangent vector to a point on a manifold, and that's called the exponential map. The subtraction of 2 points that yields a vector on a vector space correspond to the subtraction of 2 points on a manifold that yield a tangent vector, and that's called the logarithmic map. So this translation is everything the users need to know to have a basic understanding of what's going on. And as such, they can call these operations. For example, with code that you can see here. So here we're going to consider Riemannian geometry. So everything depends on the metric here, but we also have affine connections. So the geodesic between, the geodesics, that is the generalization of a straight line from an initial point with an initial tangent vector, is what's on the first third of this code. Then you see the exp, which is the exponential map, which is the operation that generalizes the addition of a vector to a point, now adding a tangent vector to a point to reach another point. And this is what is shown on the right there. You have the tangent vector in black that is added to the blue point, and we get the endpoint in orange. And lastly, the reverse operation, which is the logarithm. So subtracting 2 points, or subtracting the orange point to the blue point to get the initial tangent vector. So that's the user's perspective. Example of how it looks like for the 2 models of shapes that I had introduced. So let's say we want to compute a geodesic between 2 shapes, and specifically 2 curve shapes. This can be done with this code that you see on the top left, where first I instantiate the curves manifold, and then I take its metric. So the Riemannian metric is a specific metric on shape spaces called the square root velocity metric. And then I can compute a geodesic in the shape space of curves, which in this case represent cancel cells, which is what you see on the right. So the start curve is the blue cell, the end curve is the red cell, and all the gray contours that you see represent all the curve shapes that we encounter when we move along a geodesic in the shape space of curves. So that's an example for a manifold that is a quotient space in the case of the shapes of cells. And in the case of the Lie group, let's consider the Lie group called the spatial Euclidean group. So the group of rotations and translations. Again, I can instantiate the Lie group. So for example, I consider SE3, the spatial Euclidean group in 3 dimensions. I take one Riemannian metric defined on SE3, for example, what's called the left canonical metric. And then similarly, I can use the API metric.geodesics and compute the geodesic between 2 SE3 elements that are represented as oriented and positioned 3D frame on the red. Moving to the contributor perspective. So now, how are these operations coded behind the scene? So I'm gonna say a few words about the implementation of the geometric part, mostly. The learning part uses the translation strategy and published methods in the field. So let's look at what is a manifold more precisely. A manifold is a space that is locally, or a diffeomorphic manifold is a space that is locally diffeomorphic to Rp. And it can be described in different ways, which is interesting because these different ways of describing a manifold or specific manifold can lead to different implementations of that manifold. So the more widespread, I think, description of a manifold is through an atlas, what's described here in blue. And an atlas is a set of charts around each point of the manifold that basically make the fact that the space is locally diffeomorphic to Rp more concrete. As opposed, I think, to SageMath and the manifolds part of SageMath, Geomstats does not have this implementation of manifold as atlases. There are some contributors that say they want to include it, but we do not have it as of now. Rather, we use other implementations of manifolds. So some manifolds can be conveniently described by an immersion. Some manifolds can be conveniently described by submersion. And so we use these facts to implement different manifolds. So for the immersion part, we actually have only open set manifold implemented. So if you consider a Euclidean space and an open set of that Euclidean space, then this open set represents a manifold that is immersed in the Euclidean space that contains it. So that's an open set is a special case of a manifold described by an immersion. And so open sets that are these special manifolds are implemented in Geomstats using this immersion. The second special manifolds that we implement in Geomstats are the ones that are described by a submersion. In other words, by a set of constraints. We can also say that such a manifold is a level set. So the typical example of this case would be the sphere, that is a submersion, or a level set, for example, that's described by the green box on the right, where you have a one-dimensional sphere, also called a circle. The circle, each of these circles is a manifold, each of them represented by the pre-image of a radius. And so there are each of these manifolds is a level set for the level corresponding to the radius. So more generally, any manifold that can be represented by a submersion is included in Geomstats because we have this pre-image construction available. And then other manifolds can be created by looking at combinations of the above, which leads us to build manifolds that can be constructed from products. Skip this. So these are the manifolds that are coded in Geomstats. And you can see that some of them are rather abstract, whether others are more concrete. This hierarchy actually represents the object-oriented implementation of differential geometry present in Geomstats, where manifold is a parent class. So it's at the top of the hierarchy. It has some child classes, such as level set and open set that I've just mentioned. And then if you go down this hierarchy of classes, Python classes, go down just to the least, you can see, for example, here we have the hypersphere. Hypersphere is a child of the parent class level set, because we chose to implement the hypersphere as a level set. And level set itself is a particular implementation of manifold. And this is true for all the other manifolds that are implemented here. Interesting to physicists, maybe we have the fiber bundle at the bottom left. Also want to mention that while most of these manifolds have closed forms for the expression of their basic operations, so that exponential, logarithm, parallel transport, and geodesy computations, some do not, especially the abstract level set class or the open set class, maybe just the abstract level set class. And but the closed form do not exist. We relied on automatic differentiation because we relied on AutoGrad, PyTorch, and TensorFlow that have automatic differentiation, which is interesting in the context of differential geometry. So that's what's coded in Geomstats in terms of the spaces. All these spaces inherit from manifold because they are all manifolds. In terms of the geometric structure, we have a second hierarchy that exists, and that's linked to the metric structure that we can put on the manifold. So at the top of this hierarchy, you have affine connections. The next child is the Riemannian metric that includes pseudo-Riemannian metric. And then you have all the different types of Riemannian metric or pseudo-Riemannian that inherit from this abstract Riemannian metric class. And all the childs there are special metrics that we may be interested to use to equip our manifold, depending on what shapes we're interested in. So at the bottom left here, you can see we have, for example, 4 different Riemannian metrics that we can use to equip the manifold of the SPD matrices. I'm going to go fast on the application. I'm just going to say a few words here. Our research, in parallel to the development of Geomstats, is to basically fill this table. So this table has a few rows, a few columns, and is related, could be seen as a design document for Geomstats, because the different rows, Riemannian, pseudo-Riemannian, affine connection, etc., represent the different geometries that are implemented in Geomstats, whereas the different columns represent the different fields of statistics and learning that exist, for example, implemented in our scikit-learn. Now, our goal is to be able to apply any types of learning algorithm on any data space that has any geometric structure. So in other words, the game is to fill this table, which is what my research and the research of my lab has been interested in doing. And you have a few examples here. I'll skip through this, sorry for the use case, but this use case is available in the tutorial on Geomstats. So you actually have the full code, the data, and the results of the analysis in the notebooks folder of tutorial of Geomstats, so I can skip on that. This research is made possible by our team at the BioShape Lab at UC Santa Barbara, including PhD and postdocs. And I thank you very much for your attention. Happy to take any question.
Thank you very much. So we've got plenty of time for questions and comments.
Hi, if it's all right to ask something. You mentioned, obviously, you've got this nice table that you sort of want to fill out. Obviously, when we have some manifolds, we also have complex structures on them, like, the sphere that you gave us in the beginning. Is there any sort of, plans or ideas of what could be used to sort of incorporate that information anyway in the learning?
So I didn't hear everything you said. You have complex structures. I didn't hear the next few words. Do you mean, what do you mean by complex structures?
Yeah, so the sphere, everything you dealt with here was real manifolds. So manifolds with the base field being real. Obviously, the sphere and some other manifolds, we can treat them as complex manifolds. Mm-hmm. Is there any sort of plans or any sort of ideas of how that might be useful in the learning process? Yes,
so it has started as of last April. We have an Hermitian structure, Hermitian.py module that has been introduced, and there is some interest in doing statistics on SUM. for application in deep learning, actually, but I'm sure it could be interesting to particle physicists. Is there a plan? Yeah, there is a motivation. I'm very interested in including this. I know of 3 contributors that are interested in including this. Now, all of these contributors are academic researchers that do not have that much bandwidth to contribute to open source at this moment. And I think we still need to think about the optimal strategy for including the complex case, because I mean, we could think of representing, like using copies of 2 real spaces, but I'm not sure that will be the best way of doing that. Additionally, we want to be able to support 4 backends, and I am not an expert on how complex numbers are handled in PyTorch or TensorFlow. Last time I checked, which was 2 years ago, not all the computation available for real numbers were available in Torch tensors that would be complex. So there is a motivation. I think we still need to find contributors and to wrap our heads around the design doc.
Brilliant, thanks.
And by the way, if you're interested in helping us, we will be more than happy.
Cheers.
Eric?
Yes, thank you for this very interesting talk. I'm sure we can gain a lot of inspiration for manifold module in SageMath. My question regards the way the computation are done. I mean, when you compute, for example, the fresh mean or things like this, so this is numerical computation at the end. Do you have various backends? Is it Python floats? What are you using for the basic computation? I mean,
yes. So yes, it's all numerical, nothing symbolic. So currently, NumPy backend is in floats 64. Torch and TensorFlow are in float 32. Autograd, I forget, I think float 32. We had chosen that because the defaults for deep learning users of PyTorch and TensorFlow is float 32. Now, this has led to some problems for the continuous integration of the package, because obviously you don't have the same precision if like a fourth of the library is tested in 64 and the other 3/4 are tested in 32. So we are moving towards having everything tested in float 64 and let the user take the risk if they want to use it in 32. If we get more resources, more engineers on this on Geomstat, then we'll provide the test in both precision 32 and 64. But at the moment, the plan is to move everything to 64.
okay, thank you.
Thank you.
I have a quick question on the automatic differentiation part. So you're saying you can handle custom user provided manifold and metrics when they are presented, for example, as level sets and so on, and then AD does the job of providing, I guess, the metric and the higher order information that you need. So do you see a way to also include symbolic interactions there? You know, what if part of these things are given already as, let's say, closed formulas, maybe presented by, let's say, SymPy or something like this? Is there an interaction possible?
Yeah, so first about your comment, yeah, we can provide some user-defined manifold, so not any possible manifold, but for example, we have the pullback metric. So if your manifold is embedded in a Euclidean space or in another manifold that you know, then we can compute the pullback metric on the embedded manifold and everything that's defined by submersion, but not all possible manifolds. Yeah, symbolic computations, we haven't made any steps in that direction. I am personally extremely interested in this, especially because automatic differentiation often has numerical issues. that I think we can solve, but there is a difference between like the exponential map computed from closed form versus the exponential map that we get from integrating the geodesic equation. We haven't made any step. I don't know how crazy it would be to convert Geomstat to a symbolic version. I haven't really looked into it, but I think that would be extremely valuable, especially for numerical precision, for example. Yeah. But
So
we didn't think about it when we created the library. So now I don't know how easy it is to incorporate it. I haven't looked into it.
And so algorithms like geometric algorithms like a computation of geodesics, is this using, so basically is everything implemented from scratch in Geomstats for these things, or are you also using libraries for these kind of things?
No, I mean, so I discovered SageMath pretty late, unfortunately, a year ago. So I haven't looked at whether we could have used some things there. But yeah, basically almost everything is implemented from scratch, and you can look at this fact by looking at the requirements or the dependencies that we have to other libraries, which are pretty minimal. It's basically Matplotlib, SciPy, NumPy, I mean, the basics. So no, I
was looking at the requirements.
Yeah.
I saw you're using joblib for parallelization. Yeah. Can you say a little bit about this? I think lots of people are interested in Sage, also in parallelization for more complicated computation.
Yeah, so actually that's a very good question. Thank you. All the computations in Geomstats are possible for batches of data. So in scikit-learn or PyTorch or TensorFlow, as they are used in deep learning, you can perform computation on one data point and exactly with the same syntax on a batch of m data points. And zero axis, or the first dimension of your array representing the data, is always the number of data points that you have available. And so Geomstat follows this. We can compute n exponential maps if we are given n tangent vectors and let's say endpoints who are tangent vectors and base point, match. And so for this type of computation, since everything is independent, we can use parallelization. We don't use it too much for that specific case, actually. We have used it a lot to compute distance matrices. So matrices of geodesic distances, for example, between endpoints and endpoints. And so there we used joblib. If you have recommendations on how to use joblib, we will be interested, because we did that just because it was taking forever to compute distances, but didn't really sit and think more about this.
Yeah, I don't have a recommendation. I just learned about joblib from the requirements of Geomstats. I had made a conscious decision personally many years ago to stay away from any kind of parallel computation. But others here in the audience are maybe interested. Okay, are there any more questions or comments? Okay, if not, there's always the chat in Zulip, let's see, we are closing the session now. So thanks again, Nina, for this great talk.
Thank you very much. Thank you.
And we continue on the full hour with the next session. It's a separate Zoom session and that's going to be our Sage Modularization and Packaging Summit. We will be exploring how to bring packages, including Python packages, into Sage. This is a hands-on activity, so people can bring packages and we can work on integrating it. So starts in a few minutes. I'll announce the Zoom link on Zulip. See many of you there.